Okay, so the goal of this is to show how you can call MATLAB functions from within Python, share data between the two things, pull results from MATLAB computations back into Python. There are several ways to do this. I'm going to just show the one that's officially supported by MathWorks, but then I'm also the developer of MATLAB. But I'm also going to talk about some of the limitations of their implementation of this at the end. So here's the Jupyter Notebook, which will be on the wiki page for the how-to group in case anybody wants to actually test any of this stuff. And at the top is just a bunch of relevant links to the whole discussion. And I won't go through them one by one, but they'll be more clear why each one of these things is here at the end of this short presentation. Okay, so the first thing is you need to do a little bit of installing in order to be able to call MATLAB from within Python. We need to install something called the MATLAB engine. The Python MATLAB engine. It's developed by MathWorks to make MATLAB accessible from Python. So I've got my Jupyter Notebook here, but I've also got some terminals open here that are on the cluster. And I'm going to start from a completely new Python installation and show you how to build up getting the MATLAB engine installed. So the first thing I'm going to do is just create a new Python installation using Conda. I'm going to use Python 3.8. That's one of the supported versions of Python by MathWorks. They support all the way up to 3.9, which is the current stable release of Python, but it's only MATLAB 2021b that supports Python 3.9. And that version of MATLAB is not built on the Janelia cluster yet. It's like there's a directory for it in the MATLAB locations, but it's just empty. So 2021a, it seems to me, is the most recent accessible version of MATLAB on the Janelia LSF cluster. So I'm going to build a Python 3.8 environment. Okay, now I'm going to activate that environment. What do I call it? Python MATLAB engine. So now I'm in that environment. And now I'm going to actually, so all I've done is installed a new version of Python, totally like, you know, naked version of Python with like no modules or anything. The first thing I got to do is go into the location of the MATLAB installation on the cluster. And in that folder is something called extern, think short for external, engines, because there's also a Java engine for MATLAB, and Python. And in this folder is a setup.py, which Python people will recognize is the way that the setup tools package in Python installs Python code. So you can just run this, and I'm going to run which Python first really quick, just to highlight that the version of Python I'm now using is the new one from the Conda environment I just created. So if I just run python setup.py install, this will build, oh, oops, I forgot. I actually have to specify the build location to be my like own directory, because it's going to try to put some things into system level directories when you do that. MATLAB engine for Python install non-default location. I totally forgot about this when I made this tutorial, but I did it when I first built MATLAB. So I'll have to edit the Jupyter Notebook. Install MATLAB non-default location. Okay, yeah, I think you just add this build and then a directory where you want the build to actually happen. And I'll say build it in my home directory. I made a little directory called how to.
Greg, do you want to build or install? Because I think if you look at the second section there, it says prefix.
Oh, that's right. Yeah, I have to do these two things.
Oh, okay.
Oh yeah, I think I just want prefix. Build in default folder and install in non-default folder. I think it's build in non-default folder and install in default folder actually is, yeah, I just want to say build here instead. Thanks, Mark. Build base how to, and then install from there. Apparently I don't have access to my own home directory. I'll just give the whole path. Groups, sci, comp soft, home, how to. There we go. Okay, so that compiled a bunch of MATLAB binary, compiled a bunch of C code that interfaces Python to MATLAB in this non-standard location that I specified, and then took those files and installed it relative to my Python installation. So now my Python installation is aware that there's this bridge between Python and MATLAB. And now I'm going to show how to actually use that in the Jupyter Notebook. So this step is optional, but I want to run all of this through Jupyter Notebook. So in my new Python environment, I'm also going to install this IPy kernel, which will enable me to add this new Conda environment to Jupyter Notebooks so that I can run code from Jupyter Notebooks using this this Conda environment. So pip is just installing IPython, which is a pretty weighty package. There's a lot of stuff. So it'll take, I don't know, another 45 seconds or something to grab all of these things and install them. There we go. Okay. So now I have IPy kernel installed in my Conda environment. And now I just want to add this Conda environment, Python MATLAB engine, to Jupyter so that Jupyter will be able to run code in that Conda environment. So instead of typing this kind of longer line out, I'm just going to copy it. But this is just saying run Python, run the IPython kernel, and in that kernel install at the user level this environment. I think that really just edits some local files to say, hey, there's this Conda environment that exists and you should support it. So I think oh, there we go. So now you'll see that in my list of kernels, so to change the version of Python, which executes your Jupyter Notebook code, you click up here. And this is all of the kernels that are available. You'll see that there's, oh, it's not listed. I'm looking at the name of the IPython notebook. I think I need to restart Jupyter Notebooks to recognize this new installation of Python. So I'm going to kill my, what did I call it? I think it's just called how to. I'm going to kill the process that's running my Jupyter Notebook and then just restart it. There we go. So this all works locally on your laptop as well. I'm running Jupyter Notebooks on the cluster, but you can do this on your laptop or workstation or something like that. So basically, this step is just to launch Jupyter Notebooks. Oh, Conda activate seeker, now bsub. Okay, so I have a new Jupyter server running that should now recognize the newly installed Conda environment. Okay, so yeah, and you see now here among all of my Conda environments, there's this new one that we just installed called Python MATLAB engine. So I'm going to reopen the notebook that has all this tutorial stuff in it. We're at this step right here where we just added the environment to Jupyter Notebooks, and I'm going to make sure that this Jupyter Notebook is running that version of Python, the one that has this new Python MATLAB installation in it. Also optional, make sure that you would install any additional modules that you need. And the only other thing I need for the purpose of the tutorial is NumPy, because you need NumPy for everything all the time. Okay, so that's all of the setup. So just recapping that, I created a new installation of Python. That's not necessary. You could do it in your existing one, of course, but I did for the sake of being clean. And then I built the MATLAB engine. I had to make sure to build this, the binary files in a non-system directory because I'm doing it on the cluster and I don't have permission to write system directories. But the installation is just in my mini Conda environment. So that's totally fine for me to write to. I added this Python environment to Jupyter Notebooks so that I can run code in that Python environment in Jupyter. Okay, so now actually using the MATLAB engine. So now what's going on in this cell? So I'm just importing the only notable import here is matlab.engine. And this is the interface that we use to call MATLAB code from within Python. And the first thing you do is you start MATLAB. So engine equals matlab.engine.start MATLAB. And the inputs I'm giving here in quotes are the exact same things that you would give to MATLAB itself. Yeah, if you were to invoke it on the command line. So if I go into the binary directory for this MATLAB installation and I call matlab.h, this is like calling MATLAB from the command line. There's a bunch of options for how you might want to launch MATLAB. Any of those options can also be provided to the MATLAB engine. So the ones I'm using here, no display, no desktop, etc., are shutting off any threads that would be submitted to process GUI related things, because we're running in Python. We don't need to see the MATLAB GUI. So I'm shutting all this stuff down to make sure it doesn't eat up CPU cycles. Okay, once this engine is created, you can run any MATLAB function that's on the MATLAB path with just a dot syntax after the engine. So this magic function is commonly used in MATLAB examples where you create something called a magic square. It's a matrix where every row and column sums to the same number. So we're going to say MATLAB create us a 3x3 magic square, and that variable is going to be encoded in memory according to MATLAB conventions. But if I want to process it subsequently using Python functions or NumPy functions, I need to pull that data out of the MATLAB variable. And this line is what does that. So I'm saying magic square, give me the data value, store that as an array, reshape it into 3x3 because I happen to know that it's a 3x3 matrix. This will be a flattened array if you don't, when it comes back from MATLAB. And I happen to know that MATLAB stores the data in Fortran order. And so I want to make sure that the NumPy array is aware of that. Now, after I've done my MATLAB computing and grabbing my data from MATLAB back into NumPy, make sure to shut the engine down. Because it's constantly running, waiting for MATLAB commands to be executed. You have to close it. So let me run this cell. This will take maybe 20 seconds or so because the MATLAB engine takes a while to launch. And that's one of the limitations of the MATLAB engine, is that every time you start it, it probably takes about 20 seconds to get set up, which if you're only doing like a few fast things in MATLAB is a real pain. But if you're running something that takes an hour in MATLAB, it's not really a big deal. Okay, and so you can see we got a result that is a NumPy array. It is a 3x3 magic square, but it was MATLAB that actually found this matrix and created this matrix. So you could replace this line with any chunk of MATLAB code.
Greg, can you show us what just magic square displays as?
Sure, I've never tried. Let's see, print.
Well, you might want another cell. I don't know if starting the engine is going to take 20 seconds.
Sure. Oh yeah, good point. Type magic square. It might even have a print method itself too. Let's see. Yeah, okay. So it's a MATLAB array of type double, because that's the default data type for MATLAB and Python arrays. And it looks like it's like linearly arranged in memory like that.
So it looks like it might know its shape. Is there a magic square that shape?
Sure. No, that's there might be a name for that. It might be like axes or whatever the MATLAB ML array object name is for getting shape. But you're right, you might be able to access those properties directly. That's kind of hinting at something I'm going to show later. So like this next cell is called passing NumPy array data into MATLAB the official but hard way. So all I did here was start MATLAB, call a MATLAB function, and then fetch the result. I didn't give MATLAB any data from Python. And what if I have something that I loaded in Python? The reason, by the way, for me that I do this is Python has a lot of tools for supporting N5 and ZAR images, and then also good tools for distributing computations over a cluster, Dask. I like to do all my input and output in Python and all my distributing in Python, but sometimes someone will hand me a piece of code that's written in MATLAB. And so I want to do all my input, output, and distribution in Python, but just run the MATLAB function on the data once it's been loaded into memory. So in those cases, I want to load a bunch of data, send a bunch of pieces of that data out to the cluster and have each one of those pieces run a MATLAB function. Okay, so this cell imports, there's a new import here. It's just MATLAB, not MATLAB engine, but we're still doing the same thing we did before. We're starting the engine. This time I'm creating a NumPy array of 1,000,000 numbers and then running a MATLAB function or converting the NumPy array to a MATLAB version that can be read by the MATLAB data. And I'm wrapping that function call in some timestamps because I want to know how long it takes for the MATLAB module to convert my NumPy data to something that MATLAB can accept. And then in MATLAB, I'm going to sum all the entries in that array and then close the engine and print out that sum. So again, this will take about 20 seconds or so. And what we'll see is the amount of time it took to convert the NumPy array to a MATLAB array, and then the number 1 million, because we added up a matrix with 1 million entries that are all equal to 1. Like I said, this is the officially supported by MathWorks way of converting a NumPy array to a MATLAB array and passing it to the engine. But I found on a great Stack Overflow question, an unofficial way, but that's much better for doing this. So this line right here is making at least one, but maybe more copies of the data in memory. So first, the NumPy arrays be reformatted to lists, and then MATLAB is copying that data and creating all of the metadata associated with a MATLAB array object. This is essentially doing that by hand. So in this cell, I'm going to define some functions that will spoof an existing chunk of memory as a NumPy array in memory as if it were a MATLAB array. And so I'm not going to go through what all of this code is, but the important part is this as MATLAB function, which takes a NumPy array as input and then determines the type of that NumPy array, determines the corresponding MATLAB type, and then modifies some of the properties of the ND array object to appear as if it is a MATLAB array object. So I'm going to run this cell just so that these functions are defined. And then the only one that I'm going to call is this as MATLAB function. So here's my next cell. This is exactly the same as the previous example that I showed, except for the line where I convert the NumPy array into a MATLAB array. Now I'm calling this as MATLAB function. So I'll run this again. And what we're going to compare here is the amount of time that it takes to convert the NumPy array in place to a MATLAB array by just modifying the metadata to the amount of time that it took to make the copy of the NumPy array as a MATLAB array. So here, 1.5, 1.6 milliseconds, and here 668 milliseconds. So you see that the official and supported way of transporting a NumPy array to a MATLAB array makes a copy in memory, which is obviously not good for either time or space considerations. But it's much better to, if you know about the structure of MATLAB arrays and NumPy arrays, just modify the metadata that's required so that MATLAB can take the in-place NumPy array and work on that instead. Okay, that's most of what I wanted to show, so those are all contrived examples. The essential thing was installing the MATLAB engine, starting it, converting data, running it, fetching your data back to Python, and those are and then closing the MATLAB engine. Those are the essential pieces. But I want to show is a real application where I've done this to run a pretty weighty piece of MATLAB code in parallel on terabyte-sized images. So a lot of multi-fish processing tools use this existing piece of MATLAB code called air localize for detecting spots in fluorescent in situ hybridization images. So I wrapped this in Dask with using the Python MATLAB engine. And all of the relevant code is in this folder called detect. First, I'll show this file, Numpy to Matlab. These are those same functions I showed you in the notebook itself that just handle in memory, in place conversion of a NumPy array to a MATLAB array object. So then in detect, this function is the equivalent of what I was showing in the notebook. So you notice I start a MATLAB engine here. I convert my input data to a MATLAB object. I run a MATLAB function on that data. I fetch the result and store it as a NumPy array, and then I quit the MATLAB engine. All the other stuff that's going on in here is just orthogonal to that objective, or like helpful things. So the air localize function in MATLAB is multi-threaded, for example, but I want to limit the number of threads that MATLAB is allowed to spawn, because I know how many cores I have available on the cluster, and I've done some multi-threading in Dask as well, and I don't want to overthread my CPU. So I'm determining the number of CPUs the job has available, and I'm limiting what MATLAB is allowed to execute. But I'm calling this function in MATLAB maximum number of compute threads, and then I'm making sure that the air localized code itself is on the MATLAB path. And then everything else, like I said, is just sort of orthogonal to the objective of running air localized. Once I have my result back, I want to do a little extra processing on that data and then return it. So this is Python calling MATLAB, doing memory conversion in a smart and efficient way. And the last piece of this that I want to show is the distributed part. So the actual data I want to run this on is a ZAR array or an N5 array on disk, which is terabytes in size. So I want to take this function, which runs MATLAB in Python, and distribute it on blocks for that entire ZAR array. So that's all done in this distributed detect spots function, which just loads the data as a Dask array and then calls the detect spots function on overlapping blocks from that input. And no files are ever written to disk. Everything is shared in memory between the Dask workers who are processing independent blocks, and between Python and MATLAB. So there's no additional time or space wasted writing files to disk, reading files back off of disk, things like that. And the final result is having all of the detected spots for the entire image in one NumPy array that you can continue to process just in your Jupyter notebook, without having to load any files or aggregate results on independent blocks or anything like that. Okay, so that's a real application of the sort of contrived stuff that I showed above. I mentioned at the beginning, there's more than one way to run MATLAB via Python. The officially supported by MathWorks version that I'm showing you is only one of those ways, and it has some limitations. Probably purposefully built-in limitations by MathWorks, if I'm being honest, because they don't exactly want to help Python users that much, right? They're sort of like helping people leave their own tool behind. But one of the limitations is that the maximum size of data passed between Python and MATLAB at any one interaction is 2 gigabytes. This is a place where Dask can help. So you can distribute something. If you need to pass like a very big array, you just do it in blocks. And then another major limitation is that this MATLAB engine for Python has a memory leak. So when I run this distributed spot detection on an image that is, I know, about 1 terabyte in size, the total amount of memory that gets allocated across the entire Dask cluster is more like 3 terabytes. And it's because it's not clearing a lot of redundant copies. And the MATLAB engine is leaving behind a lot of allocated memory instead of clearing it. This is a known issue. There are lots of people who have talked about it online. MathWorks knows about it and has solved it. They've provided binary files to some people to close this memory leak, but they have not fixed it at the level of the source code in the MATLAB engine itself. Probably because they're not super incentivized to like make the integration of MATLAB and Python any easier. So I do have links to an alternative way of running MATLAB and Python that I'm interested in exploring but haven't learned yet. It's called Transplant, and instead of it uses a totally different technology for interfacing the two, something called message passing that I don't know that much about. But if I ever start doing need to do more of this, like on an industrial scale level, I would consider learning that. And then I guess the other limitation I mentioned before is that it's a limited set of Python versions that are supported, but it's really the relevant ones, 2.7 and then 3.7 onward. Okay, and that's everything.
Greg, real quick question. So
Sure.
when you ask to run multiple MATLAB, send the job to multiple workers for MATLAB, how many licenses do they use? Like, is it
as many as the workers you define are. So if you when I run like the distributed air localized function, I typically, for images of our size, which are like 2,000 by 10,000 by 7,000, that's like the voxel grid size for the spot channel, I'll use 50 workers and 8 cores per worker. And so it'll allocate like maybe, I don't know, 100 licenses tops.
Okay. So
Yeah.
it sounds like it's something only is possible in Janelia probably because other people probably don't have so many licenses.
Yep, that's a good point. So
Not
I'm
really-
not.
Yeah, it's
Yeah,
one.
that's a good point. I think this is a good way of doing this if you have a cluster and a lot of Janelia or a lot of MATLAB licenses. But the distributed part, is how I'm using it. But interfacing Python and MATLAB could be useful in other ways as well.
Yeah, good point. Cool. Thanks.
I have a couple questions.
Sure.
So your conversion function that's converting the NumPy to the MATLAB array is, I assume that's predicated on a lot of assumptions that the MATLAB version is going to remain the same. And would you have an issue if they change the MATLAB version and potentially change some of that metadata? And
Yeah, you totally
you
would.
have to write a check to say, am I using the right MATLAB version?
Yeah, I think you would. I have no idea how stable this is. Like the object that you are interfacing with here is the ML array object, which I'm assuming is probably pretty stable because it's like a cornerstone of MATLAB, but you never know. Maybe they change something, in a new version and you have to update this. So that's totally a possibility. Yeah.
Okay, and then the other question was, so I've done something quite similar to this a long time ago with Perl and R, where I had an interface to the R system running in the background in the same way. Do they have one that you could use Python to R? And would R support the functions that you need so you wouldn't have to pay for a MATLAB license?
Well, so the reason I built this was to use air localize, and that's not something I can replicate. I'm not just like, hey, I want to use these 5 standard library MATLAB functions. I would just use the Python versions of them, right? Like I avoid MATLAB like the plague if I can, but air localize is a complicated piece of software with a lot of lines of code, and I can't replicate that overnight. Well, I kind of did. I wrote something called FishSpot, which does this. It's a totally different algorithm, but it accomplishes the same goal as air localize. So I have sort of a Python version of this, but I need to compare my Python implementation to published standard things. And so that's why I personally need to run air localize. But that's not something I can just easily replicate in Python. It's like, thousands of lines of code.
Yeah, I didn't know if there was maybe a version of it in R or something like that, where you could just use that.
Probably not. It's like research level software written by a guy who used to be at Janelia, and probably you were here at the same time because you've been here for a while, Timothy Leonette. And now he's at like NYU. Okay. Yeah.
But sorry, I just want to
go
say
ahead.
that license might not be a problem because we also have this compiled version. So I don't think we're limited by license for people using it outside. But that could be sensitive to versions then. So people who use a compiled version will have to pay closer attention to which version this which version this was compiled in.
And I'm not sure how to invoke compiled code using the Python MATLAB engine. I'm assuming there's a way because the MATLAB engine itself is compiled when I launch it. The air localized code is not, right? Like I put the path to the real source files, the .m files, onto the MATLAB path, and that's how I'm running it. But if you have a compiled version of air localized, presumably you just start the MATLAB engine and add the binaries to the path. But I haven't tried doing that.
You can actually create a Python package of the MATLAB compiled MATLAB code. So it's basically imported as a Python package.
That's very cool. Yep.
Yeah, it's pretty nice. But although I didn't work out how to integrate Dask with it, unfortunately. So, but that's going to be something interesting to try.
Dask is not something that I think like compile, I guess I've built a lot of Python packages that depend on Dask, but they're so environment dependent. So like the thing I try to do is to always allow Dask to default down to running a cluster on your workstation where your workers are your CPU cores or multi-processes or multi-threads. And that's what will happen by default if it doesn't find a cluster manager. So if you import one of my Dask related packages, it goes, is LSF environment in my environment? If yes, I'm on the LSF cluster, great, I'll submit resources there. If it's not in the environment, I'll default down to workstation. Like I can't remember what it's called like the Dask local cluster object. And that, determines workers to be like cores, processes, and threads on your local resources. But if you tried to run one of my packages on a Slurm cluster or an SGE cluster, it just wouldn't know what to do. It would default down to the local cluster is what it would do. And then it would try to run your local node, whatever the same node that's running the Dask scheduler, like your whatever, the same node that's running your Jupyter notebook, the whole Dask cluster would be run on that. So in order to support these types of like massively parallel cluster related tools on a wider set of environments, you just have to know the environment it's being deployed in. I don't know of a solution for this. Like computers are standardized enough now that like if you know the operating system and the type of the architecture of the CPU and stuff like that, then you can build something really general. Clusters are not. There's different managers, different hardware. So you have to do a lot of, I think, custom coding to support something that generalizes to different clusters.
I see. And also we are also very interested in using R in Python. So if someone could talk about that next time, that would be great.
Sure. Yeah. What are you guys using R for?
Yeah, because it's a lot of genomic data. Packages are written in R, and a lot of statistical analysis packages are written in R. And a lot of our stuff is in Python. So if we can, I know some like easy sense just to call R in Python, but if someone could talk about how to parallel compute and in R and some more complicated functions, R functions in Python, that would be great.
Yeah, I'm assuming that there's something similar to this, right? Where you launch a version of R that Python can do some memory sharing with. Maybe you have to make some modifications to the Python or the NumPy array objects in order for them to be read efficiently by R. But like it probably would be pretty similar to what I'm doing here with MATLAB. I am doing one thing here that's like not. So all I've done is sort of a vanilla use of the Python MATLAB engine and then a vanilla use of Dask and put them together. But there's some additional considerations that would make things more efficient. So every single worker, a Dask worker, might execute this detect box function like 9 times. Like maybe out of the 5,000 blocks that I'm giving the whole cluster, this particular worker is actually probably going to run this function like 150 times, a lot of times, right? And every time it runs this function, it sets up a new MATLAB engine and closes that MATLAB engine. So it would be more efficient to create all your Dask workers, start the MATLAB engine independently on each one of those workers, then run detect spots as a bunch of times using that one instance of the MATLAB engines. So you're not constantly setting it up and tearing it down. And there are ways to do that in Dask where you like initialize a worker with some resources already set up. So if you were going to do something really serious, like I'm going to process, 30 data sets, using my Python R or Python MATLAB integration, you probably won't want to make those optimizations. I haven't bothered to do that in my case because I'm only running 1 or 2 data sets. But if you were going to scale up, you would need to make a few changes to the sort of design pattern that I have here.